Hello everyone, my name is Khổng Thị Thu Thảo from Computing Architect Laboratory in Nara Institute of Science and Technology, Japan. I would like to talk about my project entitled Bayes without Bayesian Learning for Resisting Adversarial Attacks. In my presentation, I will give you some background of my research before going to our proposal, which are divided into three parts, including Bayesian neural network, adversarial attacks and defense methods, and Bayes without Bayesian learning algorithm. I will finish with my conclusion. I want to start by telling you about Bayesian neural network. This is a robust form of conventional neural network. It applies Bayesian method to neural network by the probabilistic distribution on model parameters. I will focus on Bayesian convolutional neural network. That's a combination of BNN and CNN. As you know, CNN is a model with fixed parameters, so each input will give one output. In contrast, the parameters are probabilities in BCNN. If we repeat the forward path t times with in input, we get t samples of output. The ensemble of t samples can improve the model performance. Recent studies have showed the vulnerability of deep neural networks by a small perturbation in images that humans cannot distinguish and a well-trained network misclassifies. As you see, an image is the panda that neural network classifies people after adversarial attack, but we can recognize pandas. It can say that the lack of robustness for deep neural network with respect to adversaries is a big challenge to security-sensitive systems that require high confidence. Due to this weakness, many effective defenses have been proposed currently. Among them, the adversarial training is the most outstanding defense. There are two types of this algorithm. The first is adversarial training by CNN. The second is adding random components into CNN and chain to BNN to train adversarial examples. We realize BCNN can improve the robustness of CNN to adversarial attacks because the uncertainty of weights will provide a powerful protection for CNN. But the computational complication and a large number of parameters make Bayesian learning difficult on both natural and adversarial images with large models. Besides, adversarial training is also a big challenge for defenders because of the high cost of generating perturbed examples and the high training cost with a variety of adversarial data. So, a big question for us is how to apply BCNN to resist adversarial attacks but avoid Bayesian learning. Next session, I would like to talk about some background. The first is Bayesian neural network. With the application of Bayesian methods for neural network, we need to find the posterior distribution of weights while we observe the data following Bayes' theorem. Bayesian inference for neural network is evaluating the posterior distribution based on the prior distribution and the likelihood function. In BNN, weights are often assumed to be a Gauss distribution, which are real values in traditional neural networks. However, the calculation of posterior distribution is intractable directly, so Blundell has taken a variational approximation to exact Bayesian updates called Bayes by Packard. This is a variational inference to find parameters of BCNN, which use Monte Carlo approach to sample weights from variational distribution. Then we will apply weight sampling for our model. Especially, we want to show the learning comparison between neural network and Bayesian neural network. As you know, parameters with single point estimates in neural network are replaced by Gaussian distribution in Bayesian neural network, so the number of BNN parameters is double. Moreover, the calculation of the distribution is intractable directly, so Bayesian learning is more complicated than traditional training. Actually, it's not easy to apply Bayesian treatment for large CNN models. Now, I would like to present my background of adversarial attacks and defense methods. Adversarial examples that fool the network use the gradient of loss function with respect to input data. FGSM is a single-step and popular algorithm to generate adversarial attacks. Step size epsilon is used to control the direction of gradient and create a small perturbation in images. Mendry proposed the projective gradient descent attack, which is a multi-step variant of FGSM. It performs the projective gradient descent iteratively to control L infinity norm between original and perturbed images. So, this algorithm can create more sophisticated adversaries. Then, if a robust defense resists PGD attack, it will be against a wide range of other attacks. As I mentioned, adversarial training is the most outstanding defense currently. However, it has some drawbacks. The first is the high cost of adversarial example generation. The second is that attack parameters should be coincident between the training and the evaluation to achieve the highest accuracy. But the assumption is unrealistic, and if attack parameters change, we have to retrain models. Additionally, we realize adversarial training for BCNN is harder than BCNN because of a large number of parameters and the high training costs. So it's really difficult for big datasets and for large networks, although it succeeded for small datasets such as C510 and small models such as PGD. Therefore, our proposed defense is based without Bayesian learning, which is easy to implement Bayesian methods for any model. My aim is the application of BCNN to resist adversarial attacks but avoiding Bayesian training. Instead, we copy weights from pre-trained CNN model to mean up the distribution on weights of BCNN, and we control standard deviation of the distribution as a model-wide hyperparameter. Our proposal has some advantages. The first is avoiding the heavy training and catastrophic overfitting of adversarial training. The second is the independence of attack parameters. And the third is the application for any model, not only CNN. Following Bayes by backup, it assumes the posterior approximation on weights to be factorized Gaussian distribution. The weights can be obtained by sampling a unit Gauss, then shifting by mean and scaling by standard deviation. We propose layers without Bayesian learning by reparameterization in convolutional layers. We also use Monte Carlo sampling to get weight sample. Weights of pre-trained CNN are treated as mean of Gaussian distribution, and we focus on adjusting variance alpha to find out the best model-wide hyperparameter. Then we can build robot model against these attacks. Our algorithm is listed as follows. In setup step, we copy learned weights from CNN to mean of weights in BCNN. We test the model performance with different alpha and choose the alpha value for the best accuracy on each model. In inference step, we generate adversarial examples by PGD Attack before implementing several forward propagation and ensemble output samples. Our experiment is conducted on C510 and ImageNet. We use fast adversarial training, that is the fastest training, and the robust defense currently to compare with our method. We apply our proposal to pre-trained model on natural and perturbed images that are ResNet 18, pre-R ResNet 18 fast for CIFAR10, and ResNet 50 fast for ImageNet. We also set parameters of PGD Attack as the table. On CIFAR10, we attack 8 pixels with 20, 50, and 100 iterations. On ImageNet, the attacks are 2 pixels and 4 pixels with 10 and 50 iterations. These are the strong and untargeted attacks that are hard for defenders. We also apply bias without Bayesian learning to on pre-trained models. The first result is seeking the best model-wide hyperparameter. We carry out the experiment with different values of variance, for example, from 0.1 to 0.9, and based on the highest accuracies on adversarial data by PGD Attack to fit alpha for each model. Following the table, we fit alpha 0.7 for ResNet 18, 0.4 for pre-R ResNet 18 fast, 0.3 for ResNet 50, and 0.1 for ResNet 50 fast. Next step, we repeat forward pass the BCNN model T times and get T output values. We implement 1, 3, 5, 10, 20, and 50 samples and ensemble output samples. As you see in the figure, after comparison between the majority voting, the maximum output, and the average output, we choose the majority voting to assess the robustness of model because the value of the majority voting is always the best. Moreover, when the number of samples increase, the performance is also grown. It can say that the ensemble plays an important role in BCNN model, and we realize the difference between the ensemble of 10, 20, and 50 samples is not too big. Then we select the ensemble of 10 samples to make the evaluation. In order to show the tolerance for adversarial attacks, I need to demonstrate the robustness of our model. On CIFAR10, the accuracy of ResNet 18 is 92% in natural images, but is almost zero in PGD Attack images. When we apply bias without Bayesian learning to pre-trained ResNet 18 on normal images, the accuracy increases by 25% without any additional training. Moreover, our proposal can improve fast adversarial training. Our method is combined with pre-R ResNet 18 fast. The improvement is 5% under strong PGD Attack. That's 8 pixel perturbation in 20, 50, and 100 iterations. ImageNet is the big dataset with complicated images, which is classified in 1,000 labels. So we assess the performance of pre-trained ResNet 50 on natural images and pre-trained ResNet 50 fast on 2 pixels and 4 pixels adversarial images in the top 5 accuracy. Although we use learning parameters of CNN on normal images, our algorithms rises by 45% accuracy. Furthermore, applying w.rt to pre-trained ResNet 50 fast 2 pixels and 4 pixels can enhance the accuracies about 3%. Besides, because of the dependence on attack parameters, fast training declines the performance of model with large adversaries. Here, fast 2 pixels is not good for 4 pixels attack and vice versa. In contrast, fast 2 pixels with proposed BWOBL is always the best. It means we don't need to retrain model, but have a still good defense to other attacks. Finally, I would like to conclude our research. We constructed the CNN model by using learning parameters of CNN and proposed bias without Bayesian learning against adversarial attacks without additional training. Our algorithm can be easy to integrate into any pre-trained CNN on natural and perturbed images to generate a robust BCNN model. Our method increased 25% in top 1 of CFA10 and 45% in top 5 of ImageNet when using pre-trained CNN on natural images, and improved 5% in top 1 of CFA10 and 3% in top 5 of ImageNet when using pre-trained CNN on adversarial images. As you see the table, our proposal can solve the drawbacks of adversarial training by CNN and BCNN. Our method builds BCNN on large models but doesn't cost the training and still resists to strong adversaries. Actually, attack parameters are unknown and change day by day. Then we need a robust technical as Bayes without Bayesian learning to resist a variety of adversarial attacks. That's all for my presentation. Thank you for your listening.